de Colombia, Uptc, Sogamoso, we welcome you to the dissertation of the PhD proposal entitled Experimental Characterization of a UAV to Infrastructure Channel in Low and Medium Bands of 5G, presented by student Juan Carlos Muñoz Pérez, under the supervision of professors Germán Antonio Fernández and Lorenzo Rubio Arjona. This dissertation has been scheduled by the academic board of the doctoral program in engineering. It is led by Professor Germán Antonio Fernández as academic coordinator of this program, as well as Professor Jorge Enrique Espíndola Díaz, who is the head of the Sogamoso faculty. We also welcome Professors José María Molina, Vincent Miquel Rodrigo, and David Saldaña. Professor Rafael Torres is not with us today, as reviewers of Juan Carlos' proposal, as well as the rest of the attendees that are with us via Meet. We suggest you to turn on the captions that are available on the Meet toolbar, and of course, all people that follow this stream via YouTube can do the same process, all right? So, good morning, Engineer Juan Carlos, dear Juror David Saldaña, advisors Germán Antonio Fernández and Lorenzo Rubio, and good afternoon, dear Jurors José María Molina and Vincent Miquel Rodrigo. Welcome again to this event. I'm going to start sharing my screen. We're going to introduce Engineer Juan Carlos, his advisors, and the evaluation committee. So, I'm going to start presenting my screen over here. Okay. Good, so let's begin with Juan Carlos Muñoz Pérez. He received a bachelor's degree in electronic engineering from Universidad Pedagógica y Tecnológica de Colombia, UPC, in 2005, and a master in science in telecommunications from Universidad Nacional de Colombia in 2012. He is currently a professor at Secretaría de Educación Sogamoso. Since 2019, he is a student of the engineering doctoral program at UPTC. His main research interests are wireless communication, unmanned aircraft systems, drones, and propagation measurements. We have Professor Germán Antonio Fernández, holds a bachelor's degree in electronic engineering from the Universidad Autónoma de Colombia. He holds a master's degree in electrical engineering from the Universidad de los Andes and in industrial automation from the Universidad Nacional de Colombia. He is also a master in systems and communication networks and a doctor cum laude in telecommunication from the Universidad Politécnica de Valencia. He is currently a full professor at the Electronic Engineering Department at Universidad Pedagógica y Tecnológica de Colombia. His research interests include wireless communication and propagation modeling. His current research is focused on channel measurements and modeling vehicular-to-vehicular communications. Lorenzo Rubio Arjona received a PhD degree in telecommunications engineering from the Universidad Politécnica de Valencia, Spain in 2004. In 1996, he joined the communications department at the UPV, where he is now full professor of telecommunications engineering. His main research interests include radio wave propagation, ultra-wideband systems, vehicular communications, and millimeter wave propagation. The first juror is Dr. José María Molina. José María Molina García Pardo received a bachelor's degree in telecommunications engineering from the Universidad Politécnica de Valencia, Spain in 2000. The master's degree in communication and signal processing from Newcastle University, UK, in 2001, and the PhD degree in telecommunications and the Bachelor of Business and Administration degree from the Universidad Politécnica de Cartagena, Spain, in 2004 and 2008, respectively. In 2001, he joined the Department of Information Technologies and Communications at Universidad Politécnica de Cartagena, where he is a full professor since 2016. His research activities are centered on radio communications, propagation, channel modeling, and experimental channel sounding in different frequency bands and technologies. Dr. Vincent Miquel Rodrigo Peñarrocha received a master's degree in telecommunications engineering from the Universidad Politécnica de Madrid, Spain in 1990, and the PhD degree in telecommunications engineering from the Universidad Politécnica de Valencia, Spain in 2003. He joined the Departamento de Comunicaciones, Universidad Politécnica de Valencia in 1991 as a lecturer. His current interests include radio wave propagation, antenna measurements, instrumentation, virtual instrumentation in laboratories, and any educational field. We also have over here Dr. Rafael Pedro Torres, Universidad de Cantabria, Spain. He received a master's degree in physics from Granada University, Spain in 1986, and the PhD degree in telecommunications engineering from the Polytechnic University of Madrid in 1990. He became an associate professor with the Department of Communications Engineering, Universidad de Cantabria, Spain, where he is currently a full professor in signal processing and communications engineering. His fundamental lines of research have been in the development of numerical methods for the analysis and design of antennas, the applications of high-frequency techniques for simulation and the analysis of the radar section, as well as the design of radar systems. also count with the participation of Dr. David Saldaña. David Saldaña received his bachelor in 2010 and master's in 2012 in informatics engineering from National University of Colombia, and his PhD in computer science, artificial intelligence and robotics at Federal University of Minas Gerais, Brazil, 2017. He is an assistant professor in computer science and engineering at Lehigh University. He worked as a postdoctoral researcher at the GRASP Laboratory, University of Pennsylvania. His main research interests are focused on modular aerial robots, multi-robot systems, and robot swarms. His current projects include enhancing resiliency in large-scale robot networks and co-designing algorithms, dynamical models, and robot hardware for modular robots. And finally, we have Dr. Wilson Javier Pérez Holguín. As part of the academic board, he received a bachelor's degree in electronics from the Universidad Pedagógica y Tecnológica de Colombia in 1999, a Master of Science in Industrial Automation from Universidad Nacional de Colombia in 2006, and a doctorate in engineering from Universidad del Valle in cooperation with Politécnico de Torino in 2012. Since 2005, he has been enrolled with the Electronic Engineering School, Uptc, as a full-time professor. He is the author of 2 patents and numerous scientific papers. His research interests comprise a microprocessors design test, fault-tolerant systems, parallel computing, embedded systems, and robotics. Okay, thank you everybody for listening over here. So in this moment, I'm going to stop presenting, and let's continue with our event. The methodology for this dissertation consists of 3 stages. First, Engineer Juan Carlos will have 30 minutes to present his proposal. Second, the reviewers participating in this dissertation can ask Juan Carlos questions to confirm that he addresses their suggestions and observations. Later, attendees with a PhD can also take part in this stage. And finally, at the end of the question time, Professor Germán Antonio Fernández, as advisor of Engineer Juan Carlos, will have time for a brief feedback as well. Only the first stage will be streamed via YouTube, and later on we will continue on Meet, all right? So now we invite Engineer Juan Carlos to start his presentation. Welcome, Juan Carlos, and the word is yours.
Thanks, Teacher Johan. Good afternoon, Dr. José María Molina, Dr. Vicente Miguel Rodrigo, and Dr. Rafael Pedro Torres. Good morning to Dr. David Saldaña, professor and partners of our doctoral program. Thank you for attending the presentation of my doctoral proposal entitled Experimental Characterization of Unmanned Aerial Vehicle to Infrastructure Channel in Low and Medium Bands of 5G, which is the result of the process based on the evaluator's suggestion, the related work in channel characterization, the orientation of my advisor, and joint work with the Telecommunication Research Group and the Electromagnetic Radiation Group of the Universidad Pedagógica y Tecnológica de Colombia and the Universidad Politécnica de Valencia, Spain, respectively. This is today's agenda. First, we will make a contextualization of the issues that are immersed in the proposal. Then, we will describe the motivations, opportunities, and preliminary limits of the proposal. Next, I will explain the literature review process, the state of the art, and the related works. After that, I will talk about the research problem and the proposal's contribution will be described. Then we'll show you the objectives and methodology. And finally, I will describe the expected results of this proposal. Although 2020 was a difficult year for everyone, the rapid development of emerging applications such as artificial intelligence, Internet of Things, virtual reality, and three-dimensional media have resulted in a rapid increase in traffic, where at least half is attributed to mobile devices. The wireless communication technologies that initially support most of the novel applications lie in the industrial, scientific, and medical ISM-ready bands portion of the spectrum. The basis for optimal development of all these systems and applications are those to come is the characterization of the channels used to propagate wireless signals. A well-defined propagation model could help the application developers and system designers to enhance the communication systems. In recent years, research work has been carried out in the vehicular propagation scenario. Given the dynamics of the channel, the mobility of vehicles, and the scattering objects, since they increase the effects of fading by temporal scattering and Doppler characterizations of different links of the so-called vehicle to everything scenario have been carried out They have allowed the development of dedicated short-range communication, the IEEE 1609 series of standards that can support the direct connectivity to other vehicles, or B2B channel, or vehicles to infrastructure and IT's application scenarios, whose basis is the characterization of the particular fading phenomena of these links. Fading is the phenomenon that most impacts wireless channels. It can be modeled through a long and short-term approaches, path loss, shadowing, and time frequency dispersion model. A good characterization process must consider multipath and Doppler effects and the selectivity dispersion duality. That is one of the essential properties of this type of channel. Now, I will present the motivation. As in the bit-to-everything scenario, an UAV to everything scenario has been proposed that has been derived for the mobile ad hoc networks through vehicle ad hoc networks to flying ad hoc networks that allow some UAV communications without infrastructure. Here, we can find various types of channels, such as the UAV to pedestrian channel that focus on the use of the technologies of the ISM bands. This UAV to UAV channel, this channel is the basis of the flying ad hoc networks and multi-UAV applications. The UAV to infrastructure channel is thinking about the integration. This channel is thinking about the integrations with mobile networks, and also there is the UAV to network channel for the future. Considering the experience of the telecommunication group for our university and the electromagnetic radiation research group for the UPB in the areas of the experimental characterizations of channels and following the development of the P2X environment, our motivation is to contribute to the characterization of the UAV to infrastructure channel and the standards and application for these types of vehicles and applications. Although currently the communication system for UAVs drone type have been adapted to the technologies available for ISM bands, the 5G technology will support emerging new use cases, such as a precise ground-based navigation service for UAVs of drone. Moreover, technical specification for remote identification of unmanned aerial systems will be completed in the 5G phase 2+. In addition, among the essential characteristics of this technology is support mission-critical application necessary in US systems. Identify the path loss of an unmanned vehicular system is critical for determining the link budget and is essential for planning and rolling out new 5G use cases. Then we find new research opportunity developing propagation model for UAV integration with 5G and the next 6G technology. To define the proposal, the International Telecommunication Union has determined the spectrum used by the IMT 2020 of 5G technology as we know it. This organization has agreed to have frequency in low, mid, and high spectrum ranges. So 1 GHz low bands are oriented for coverage in large-scale areas. In the World Radio Communication Conference for 2015, mid bands were defined as the 3.5 GHz range, including the mid one. Currently, high bands were recommended in the World Radio Communication Conference from 2019 to meet the ultra-high band broadband speeds envisioned for 5G. The first commercial deployment of 5G technology have been carried out in the 3.5 GHz range in urban environments, looking for a balance between coverage, bandwidth, latency, and capacity. This doctoral proposal will be focused on obtaining IMT 2020 modeling channel in low and mid bands for UAV to infrastructure communication in typical urban, suburban, and rural operating environment zones. The 5G 3.5 GHz and the 850 MHz ranges will be used for the experimental measurements to develop a propagation model for UAV, which could be offered a good mixture of coverage and capacity performance. Regarding the literature review, seeking to have a better understanding the scientific community contribution to the characterizations of wireless channel for UAVs and 5G application, we carried out a careful review of a state of the art by first making a network map in the main themes of the proposal, making an intersection with the environments and type of vehicles used. This literature review was carried out through a systematic review based on Prisma methodology. First, by defining 3 equations for IEEE, Web of Science, and Scopus database. Then, we did a separate search for words related to the proposal main topics, followed by an analysis of the intersection of the results with the environment and the UAV type limitations. The most relevant papers were referenced in the proposal, and the process of identifying the new ones will continue. The review of state-of-the-art allowed us to establish the approach for the characterization of the UAV to infrastructure channel. This proposal will be based on the stochastic and physical model, focusing on the non-geometric stochastic or parametric stochastic model without assuming any particular geometry, obtaining a mathematical representation of the response of the wireless channel, including all its parameters that are then determined through the analysis of the data obtained through the experimental campaign. Compared with theoretical and simulation-based modeling methods, measurement-based stochastic channel modeling has the advantage that the channel observation acquired during the measurements are close to the channel experienced by a piece of user equipment in realistic application scenario. Here, we can see the relationship between different channel models according to the accurate versus simple or physical versus analytical category. It is illustrated that although analytical models are general, they do not accurately describe the channel's behavior. In this figure, we make a classification of the related works. Here, the papers have developed propagation model for the UAV to infrastructure channel have been classified by 5G frequency bands in which they have been validated. This figure shows the type of analysis performed for large and small-scale fading effects. In summary, the need for more measurement campaigns to propose or validate propagation models science in the bands of interest of 5G technology can be observed. Science UAV currently use IS-in band frequency bands to communicate. Most of the work carried out is located here. We have selected the 5G mid frequency band located at 3.5 GHz to perform the characterization of the UAV to infrastructure channel, taking into account it is an open research problem, since the EU recently assigned it for the preliminary deployment of 5G technology. This recent assignment is one reason why no experimental model has been proposed for this band, and where more measurement campaigns are required. It also been proposed to carry out the experimental characterization in low bands at 850 MHz, since there is enough literature to compare and contrast the works carried out. Some of the most relevant papers found in the literature review were condensed in a table where works were classified according to the experimental characterized frequency band, the channel sounder used, and the proposed propagation model. In this work, we can see works in the ISM bands and 5G low bands, as well as some works in the high bands using simulation software. In the papers, the models were restricted to particular features such as speed, the altitude of the drone, and the stations. We conclude that the channel sounder is an essential factor for a good definition of a propagation model, and it can limit the extraction of propagation parameters. For example, Professor David Matlack developed a correlated channel sounder to obtain propagation model to characterize small-scale fading effects and path loss exponents. In our proposal, we will develop a pseudo-noise correlated channel sounder to obtain path loss, shadowing, and smell escaping models in low and mid bands of 5G. Regarding to the research problem, the challenges and requirements of the proposed propagation model to be developed have been synthesized in this graph. These have been generalized in 5 aspects: the physical approach, the dynamic aspect, the 5G applications, the propagation environment, and the non-urban wideband approaches. These aspects present challenges that must be overcome for development of the proposal. First, the physical approach selected is the non-geometrical stochastic model or parametric stochastic model that will require developing a wideband channel sounder and running an extensive measurement campaign. The object is to propose path loss model and time frequency dispersion model. Regarding the dynamic aspect, there are those inherent to the dynamics of the vehicle, the 3D movements, and the maneuverability limits of the drone that must be defined when planning the measurement campaign. Another dynamic component is the channel which, in addition to presenting noise and interference, will present us with the challenges of including the variation in altitude and acceleration of vehicle in the proposed model. The 5G low and mid-frequency bands will help define the channel sounder. The propagation scenarios to be characterized will be urban, suburban, and rural under line of sight or non-line of sight condition. Finally, the narrow band and wideband approaches will allow the long and short-term fading effects to be described through path loss, shadowing, multipath, and Doppler effects, and Doppler models. Overall, developing accurately propagation model for the UAV to infrastructure channel in the low and mid bands of 5G will be the challenge. Defining the problem allow to establish the following research question: how to perform an experimental characterization of a UAV to infrastructure channel in the low and mid frequency bands of 5G technology in urban, suburban, and rural environments. This research question proposed work to expand knowledge since the experimental characterization of UAV channel to infrastructure is an open problem. Other more specific research questions to which this doctoral proposal will answer are how to implement a wideband channel sounder to carry out a reliable measurement campaign on UAV to infrastructure channel. Another asking is how to develop an experimental path loss propagation model in UAV to infrastructure channel operating in the band selected in the environment selected. And also we have how to develop channel models of time frequency dispersion operating in the low and mid frequency bands in the environment selected and the conditions selected, especially non-line of sight conditions. The following hypotheses are proposed considering the research question. The experimental characterization of a communication channel between the vehicle will allow estimating coverage and wideband UAV parameters in the environments selected. The propagation models obtained will be characteristic of the environments in which the measurement campaigns will be carried out in a limited to parameter altitude, speed of movement of the accelerations, and the vehicle's antenna characteristics. The line of sight of channels will depend mostly on the forms of the movements of the UAV in rural areas. In the other areas, we hope the most significant multipath will be products of the terrain obstructions and buildings. The channel sounder synchronization is a problem to resolve. For that, the channel sounder can be implemented with radio card, split spectrum pseudo-noise sequences-based sounder, all of them portables and turned to the research band of interest. Of course, it will be necessary to include shared reference and processing algorithms on board of the UAV for the non-loss condition especially. According to the research problem and the hypothesis, my main objective is to perform an experimental characterization of a UAV to infrastructure channel in low and medium bands of 5G. And my specific objectives are to design and implement a channel sounder in 850 MHz and 3.5 GHz 5G ranges, with possibilities for carry out portable wideband measurements on a UAV to infrastructure channel. The second specific objective is to develop a propagation model to describe the performance of the path loss in the channel under study from the processing of signal string instrument collected in the measurement campaign in the selected environments. Analyze the path loss, Doppler effects, and fading static parameter contrasting them with the results obtained in the low and medium band of 5G will be the third specific objective. And the last specific objective will be to analyze the effects of multipath time delay spread in UAV to infrastructure channel to obtain channel models of time frequency time dispersion, taking into account the wideband channel sounder resolution parameters achieved. As can be seen, the first specific objective requests to develop the wideband channel sounder. The second specific objective proposes the development of large-scale model. The third specific objective attempts to contrast the results and obtain another parameters for the measurements obtained. And the last objective is related to obtain the small-scale parameters. Regarding to this, the methodology to this proposal is an experimental type research that proposes path loss propagation model in UAV to infrastructure channel in urban, suburban, and rural environments. To achieve the defined objectives, it proposes to divide the project in 4 stages, developed through applied and experimental research approach and a quantitative and correlational methodology, validating the results in the selected environment to perform the characterization of the wireless communications channel. The stage 1 was named Channel Sounder Specification and Implementation. The stage 2 was named Path Loss Characterization. The third stage was named Fading Characterization related to the movement of the vehicle. And the last stage was named Time Delay Spread Characterization, or to analyze the multipath effects. The first stage will be conformed by 5 activities. The fifth activity is establish the design parameters for the wideband channel sounder, the chip rate, emission power, coherence bandwidth, and so on. Also, of course, the georeference system that is an important specification. Identify the appropriate equipment to implement the channel sounder according to the design specification. Select the UAV type drone that allow the implementation on this type of equipment. Define the polarization and location antennas, and determine the characteristics of the UAV control that might interfere with the experimental measurements of the in the environments and in the channel select. The second stage is the largest because it includes the measurement campaign and the development of the large-scale model. Will be conformed with 8 activities. The first activity will be identify the particular characteristic of the scenario. Second activity is related to determine the procedure to operate and measure the propagation parameter. Parameterize the variables and power balance of the channel sounder will be the third activity. And of course, plan the measurement campaign and do the measurement for calibration. The other activity for this second stage are carry out the measurement campaign in the environments and conditions of line of sight and non-line of sight expected. Process the data obtained, determine the path loss exponent taking into account the conditions selected, and develop a propagation path models according to the conditions selected. The third stage will conform by 3 activities. They are analyze the path loss exponent achieved in the previous stage. Compare this analysis and results of the short and long-term fading generated in the different working bands and the second order statics. Attempt a validation of the path loss propagation model with ray tracing techniques in a controlled environment. This activity is a longer activity. This is the reason because this stage only have 3 activities. And the last stage have 4 main activities, which are related to the small-scale models. The first principal activity is obtain the power delay profiles and the multipath parameters. The second stage is attempt validation of these small-scale parameters through ray tracing techniques in a controlled environment, and the activities required by the doctoral program. We propose developing these activities in 30 months under this schedule. However, these are tentative periods because right now we are carrying out a process of achieving a double doctoral degree with the Universidad Politécnica de Valencia. The stage proposed are related to the methodology above mentioned, and currently I am defining the equipment to conform the wideband channel software. Related to the expected result, we have the implementation of wideband channel sounder on the range selected, proposed propagation model related with the large scale parameters, proposed large scale models to describe both Doppler and multipath effects in a UAV to infrastructure channel. Also, contribute with more realistic propagation model to assist in the transmissions and reception evaluative techniques, deployments of network and simulation of the UAV to infrastructure channel. Finally, is it worth mentioning that this proposal is supported by the scholarship called National Program of Doctoral Excellence of Bicentennial. Also, I would like to thank the evaluators for suggestions and comments on the proposal. Thanks everyone for your attention.
Okay, thank you, Juan Carlos, for presenting your proposal, for sharing with us this experience. On behalf of the doctoral program in engineering and the electronics engineering graduate school, we thank everyone who followed this presentation via YouTube. We are very committed to our academic processes and our research oriented towards solving contextual problems. Our doctoral program promotes three fundamental pillars: research as a route to find solutions to local problems with a global view, self-management that encourages the autonomy and self-confidence of our students, and networking that promotes collaboration with the international community. We hope that you all have enjoyed this event and that its content has been meaningful to you. Thank you very much, and we hope to see you in the next time.